For thousands of years, humanity looked at the world and asked, if I take this rock and smash it, I get pebbles. If I smash the pebbles, I get sand. If I smash the sand, is there a point where I can't smash it anymore? In school, you were given an answer. You were told that everything stops at the atom. You saw a diagram that looked like a mini solar system, a nucleus in the middle, electrons whizzing around. That diagram? It's a lie. Well, it's a useful lie, but it's wrong. Because if you look closer, the solid stuff in the universe dissolves. The proton isn't a hardball. It's a chaotic ocean of energy. And the electron? It's not a moon orbiting a planet. It's a ghost. Today, we are going to descend into the quantum realm. We are going to meet the real building blocks of reality, the Standard Model, the particle zoo, and we're going to answer the ultimate question. What are we actually made of? Before we meet the particles, we need to understand the scale, because our brains are terrible at understanding small. Imagine this football stadium is an atom, the whole thing. The electrons will be the cheap seats way up in the nosebleeds. And the nucleus, the part that contains 99.9% of the mass, it's this marble in the center. Everything between that marble and the nosebleed seats is empty space. You are mostly empty space. The chair you're sitting on is empty space. The only reason you don't fall through it is because of invisible force fields pushing against each other. But let's look at that marble. The nucleus. It's made of protons and neutrons. For a long time, we thought these were the fundamental pixels of the universe, indivisible. But then, we built massive machines to smash them together. And when we cracked the proton open, we didn't find a smaller hardball. We found 3 distinct points of charge. Welcome to the quarks. If you want to build a universe, you actually don't need many ingredients. You need matter, particles, fermions, and force particles, bosons. Let's start with matter. To build you, me, the sun, and a ham sandwich, we only need 2 types of quarks. We call them the up quark and the down quark. Physicists are terrible at naming things. Don't overthink it. Up and down are just labels like chocolate and vanilla. Here's a recipe for a proton. Take 2 up quarks and 1 down quark. P equals U plus D. And a neutron, take 1 up and 2 downs. And equals U plus D. Here's the weird part. We are used to electrical charge being whole numbers, +1 or -1. But quarks, they have fractional charges. Up quark has +2/3 charge and down quark has -1/3 charge. Do the math. This is why the neutron is neutral. It's just a perfect cancellation of quark charges. But here's the catch. You can never, ever find a quark alone. They are shy. If you try to pull 2 quarks apart, the energy you put into pulling them actually creates new quarks out of thin air. It's called confinement. So, we have quarks making up the nucleus. But what about the thing orbiting the nucleus? The electron? Is the electron made of quarks? No. The electron is a fundamental particle. It has no size, no structure. If you zoom in, it's still just a point. It belongs to a family called the Leptons. The electron is the celebrity of the lepton family. It does all the work, chemistry, electricity, the internet, but it has a little brother, the neutrino. Neutrinos are the ghosts of the universe. They have almost no mass, no electric charge, and they travel near the speed of light. Right now, hold up your thumb. About 60 billion neutrinos from the sun just pass through your thumbnail. They pass through the Earth, through the floor, through you, and are halfway to Mars by now. They rarely touch anything. So that's it, right? Up quarks, down quarks, electrons, neutrinos. That builds the whole universe. Nature, however, ordered extra courses off the menu that nobody asked for. Everything we just talked about is Generation 1. But for some reason, the universe has Generation 2 and Generation 3. Meet the muon and the tau. They are basically electrons, but fat. The muon is 200 times heavier than an electron. The tau is 3,500 times heavier. And the quarks have heavier cousins too. These heavier particles don't last. They are unstable. They decay into the lighter Gen 1 particles in a fraction of a second. But they were there at the Big Bang. Why 3 generations? Why not 1? Why not 10? We have no idea. We have the bricks, quarks, and leptons. But if you dump a pile of bricks on the ground, they don't become a house. They need mortar. They need glue. In physics, forces aren't magic. They are exchanges of particles. We call these bosons. There are 4 fundamental forces, and each has its own boson. Number 1, the photon. In the quantum world, forces aren't just feelings. They are conversations. When 2 charged particles attract or repel, they're actually tossing messenger particles called photons back and forth. But these photons are virtual. They are virtual because their existence cannot be detected directly, but we can detect the effect that they cause. Think of it like wind. We cannot see wind, but we can see things are being blown away by it. It keeps your electrons orbiting your nucleus. But there are also real photons. They're used in many technologies in our daily lives. You know this one. Light, radio waves, Wi-Fi, magnets sticking to your fridge. That's all the photon. It carries the electromagnetic force. One of its most significant applications is the solar cell. Sunlight is composed of visible lights, which can be seen as a stream of photons. The photon kicks one of the valence electron in the silicon atom inside the p-n junction of the solar cell. The electrons being kicked out flow through the external wire connecting each side of the junction to generate energy. Number 2, the gluon. Remember how protons are packed tight in the nucleus? Positive charges hate each other. They should fly apart. The gluon is a strong force. It is 137 times stronger than electromagnetism. Similar to the virtual photons being exchanged between charged particles, the gluons inside nucleon are also virtual. It acts like a super strong rubber band. It glues quarks together. Without gluons, you would instantly disintegrate. One interesting thing is that these quarks have color charges. It is not the electromagnetic charge. It is the charge of the strong force. It has nothing to do with the colors we see every day, but a good analogy to describe the strong force interaction between particles. There are 3 types of color charges: red, green, and blue, so that the sum of these colors becomes white. No matter how the color charges change, the net color in this nucleon must be white. In the microscopic view, the quarks change their color charges via exchanging virtual gluon particles. Look at this case. The red quark wants to swap its color with the blue quark, so it emits a gluon containing a red charge and an anti-blue charge. The anti-color charge can be seen as the negative color charge. Now the red quark becomes blue. As the blue charge absorbs the gluon, it now becomes red. These swaps of color charges happen constantly and extremely rapidly, which is about a septillion times a second. And the more interesting thing is that the gluons inside a nucleon are sometimes leaked out and are absorbed by another nucleon. The leaked gluon is transformed into a virtual pion and are absorbed by another nucleon. Whenever a nucleon emits or absorbs a pion, it changes its identity between proton and neutron, and this identity change occurs 200 sextillion times per second. So in the quantum view, a nucleon in an atom is always a superposition between a proton and a neutron. As they are constantly exchanging virtual pions, they create a Yukawa potential between them that hold themselves together. Such force holding them together is the residual strong force, or the nuclear force. This binding force is around 100 times stronger than the electromagnetic repulsive between protons. That is why the protons can overcome their repulsive force and be held together as a nucleus. Number 3, the W and Z bosons. This is the weird one. The weak force is capable of alchemy. It can actually change one type of particle into another. It can turn a proton into a neutron, which is how the sun burns. During the first stage of sun fusion, 2 protons in the sun's core collide with enough energy to overcome their mutual electrostatic repulsion. At the moment of closest approach, one of the up quarks and one proton emits a virtual W plus boson. By losing a positive charge via the W plus boson, the up quark transforms into a down quark. The W plus boson is extremely unstable and almost instantly decays into a positron and an electron neutrino. The original proton has now become a neutron. This neutron binds with the other proton to form deuterium, a heavy isotope of hydrogen. And the most significant role of the Z boson is allowing neutrinos to interact with matter without turning into other particles. Look at this case. A high-energy neutrino approaches an electron. Because neutrinos have no electric charge, they are invisible to the electron's electromagnetic field. They only see each other via the weak force. As a neutrino passes within an extremely short distance of the electron, it emits a virtual Z boson. The electron absorbs a Z boson almost instantaneously. The Z boson carries a specific amount of momentum and energy from the neutrino to the electron. After absorbing the Z boson, the electron gains kinetic energy and starts moving. In plain words, the electron is pushed by the neutrino. Number 4, the graviton. And then there is gravity. We think there should be a particle called the graviton, but we've never found it. Gravity is a rebel that refuses to fit into the standard model. As previously said, every fundamental force has its own boson. If gravity follows the same rules, there must be a particle that carries a message of gravity. We call this the graviton. To fit the laws of physics, a graviton must have very specific properties. First, it is massless. Because gravity has an infinite range, the graviton must have no mass. If it had mass, gravity would run out of steam over long distances. Second, it travels at light speed. Just like light, the signal of gravity moves at exactly 3 times 10 to the power of 8 meters per second. Third, it is a spin 2 particle. This is the graviton's unique fingerprint. In quantum mechanics, spin describes a particle's intrinsic symmetry. A spin 2 particle is required to create a force that is always attractive. If gravitons are everywhere, why is the Nobel Prize for finding one still up for grabs? First, gravity is incredibly weak. Compared to the other forces, gravity is a wimp. It takes the entire mass of planet Earth to pull a paperclip off a table, but a tiny magnet can defy all that gravity with ease. Second, detection is nearly impossible. Because gravity is so weak, an individual graviton carries an infinitesimal amount of energy. To detect a single graviton, we would likely need a detector the size of Jupiter orbiting a neutron star, and even then it would take billions of years to see one. If we prove the graviton exists, it means gravity is quantized. This would allow us to write a single set of equations that describes the entire universe, from the smallest vibrating string to the largest galaxy cluster. It is a final piece of the puzzle in our quest for the theory of everything. For decades, there was a gaping hole in our theory. We had the particles, we had the forces, but the math said all these particles should be massless. They should all be zipping around at the speed of light, but they aren't. Electrons have mass. Top quarks have huge mass. Where does the mass come from? Enter the Higgs field. Imagine the entire universe is filled with a thick cosmic snow. The photon is the bird. It doesn't interact with the snow, the field. It glides at light speed. It has no mass. The electron is the person walking. It interacts a little bit. It gets slowed down. That drag is what we call mass. The top quark is the person dragging the sled. It interacts heavily with the field. It has lots of mass. In 2012, at the Large Hadron Collider, we smashed protons so hard that we chipped a piece of this field off. That chip was the Higgs boson. It proved the field exists. It proved that mass isn't property of the object, but a measure of how hard the universe is grabbing onto it. So we have the standard model. Quarks, leptons, bosons, Higgs. It is the most precise scientific theory ever created. But it's embarrassing. That is only 5% of the universe. The other 95%, we call it dark matter and dark energy. We don't know what it is. The standard model is a map of an island, but we are realizing the island is in the middle of a massive, unexplored ocean. It's easy to feel small when you look at the stars, but look inward. You are a galaxy of particles, up and down quarks, glued together by the strong force, orbited by electrons, bathed in Higgs fields, interacting through photons. These particles have existed since the beginning of time. They have been part of stars, asteroids, and dinosaurs. And right now, they are arranged in the most complex pattern the universe has ever created. So, are protons and electrons the smallest things? No, the reality is much stranger and much more beautiful.